All right, let me share my screen. Give me a second here. Find the right layer. Oh, looks like I might have lost that layer. Yeah, okay. It's a new one. All right. Okay. All right, so we were looking at different different networks that we for the homework, right? And remember that, and I think I'm just going to write down. So if we were going to do something like, hold on, my layer is not active. Give me a second. Where'd it go? Ah. All right, here we go. So if we were going to put together a network that say had two input nodes, right? And then we had like three or four nodes and one layer, hidden layer, and another four for a second hidden layer. And then let's say we had one output. Oh, sorry, I should have done that in the yellow color. There we go. Okay, and remember what we talked about was when you talk about something being dense, it means that the previous layer, every node in the previous layer connects to every node in the layer you're calling dense. So this one here, right, if we said, to make this layer, if we said dense, and then we would say 4 because it has 4 nodes, and because it's the first layer in the network besides the input, we would have to tell it what the input shape is. Input, I think it's shape equals 2. Right? So, and that would mean dense means, of course, now every single one of these, and let's just do a color coding here. So I'm going to put this in green here. And so this guy is going to connect to every single node in this hidden layer. And then this orange, well, let's see, that's not a good color because let's do blue. And the blue one will also connect to every single node in the hidden layer. That's what dense does. It goes back to the previous layer and connects every single node to every node in that layer. Right? That's what it means to be a dense layer. Okay, now this one here, right, we have to also use dense. Okay, because if I said I want two dense hidden layers, you would use dense here as well. So you would say dense 4, and now you don't need to tell it the input shape. I mean, you could. You could say the input shape is 4 because there's 4 in the layer before it, right? And again, every single, and I won't bother with color coding here, but every single node here connects to every other node. So, right, every single node. That's what the fact that this is a dense layer means, right? One more. Running out of colors. Let's see. Gets ugly quickly. Right? And then the last thing you put in the network would be the output, which is just 1, right? So then you would just say dense 1, and again, the dense is just referring to the fact that every single one of these nodes will connect. Right? That makes sense? Right, so remember that this one here, I should have written it below. This one would go here. Right? Yeah, so that's how you would define this particular network with dense layers. Yeah.
I have a question about that.
Yeah.
So for the one, I think it was the one that you showed us toward the end of the class. It had the beginning input shape as a kind of like it had split up. It had like a flatten, so it would
Yeah,
multiply it.
right.
What exactly would the flatten be for this one?
Yeah, so okay, so here's the deal. The flatten is only used when you need to flatten the data. So if the input to this network was I don't even know because we have too little of these. Let's make another network where we have, I don't know, 16. I'm not going to draw 16. 16 inputs. Okay. So if we have 16 inputs, so this, you'd only need flatten if the input to the network is going to be some kind of image. So for 16, it would have to be a 4x4 pixel, right? So it'd be, so that's 2x2. This is 4x4, right?
Mhm.
Actually, it's not 4x4 because I haven't done it right. I didn't do it right. I didn't draw it right.
Wait, so flatten wouldn't be in our homework, would it? I mean, you know, right? We don't
Yeah,
have.
no, you didn't need to do it flatten
Okay.
for anything because the only, let me draw this again. I'm not doing this right. So we need 4 and then 4, right? So if this was an image and every single one of these boxes was a pixel, what you could do is it's like you wouldn't have to pre-process it. You could just bring the image in and then you use a flatten layer that takes the image and just flattens it out, meaning that it would take all of these pixels and instead of being like 4x4, it would be 16, right? So this first, the value in this image, this pixel, here, hold on, let me get rid of that. I want to actually put a number there. So the value in this pixel, let's say in a grayscale between 0 and 1, let's say this is 0.9. So it's very close to white, if that's what, So 0 would be black to 1, which would be white. Okay, so let's say here's 0.9, that would go in this node, right? So it would be 0.9. And let's say this one is 0.1, that would go in this node. All the way down, right? So it would flatten this out, this image out. So the flatten just means that, hey, I can put an image into the network. I don't have to actually flatten it first and then put it in. But you certainly can flatten it first, right? You can use Python to flatten it first so that instead of being a 4x4 thing, it's a big string of it's a string of 16, right? It's 16 different numbers. And they can be put into the nodes in the input. But the flatten layer just does it just does an operation on the data so that you can just put images into your network, right, directly. Does that make sense? So it's not necessary unless someone tells you that that you want your network to accept whatever an image. Like in the example for the numbers, it was 28 by 28, right? I think, yeah. Well, those 28 by 28 pixels for the handwritten numbers we were looking at, right? So you don't need the flatten layer unless you want to bring images in, right? Without having to flatten them yourself. But it's kind of nice that you could flatten them, right? The layer flattens it. So the incoming can be an image instead of like a big long string that you have to do yourself somehow before, right? You can do it in code, but I'm just saying it's a nice feature. But you don't need it, right? Unless someone says to you, hey, I want this network to take in an image and I don't want to have to flatten it. So please, can you make the network flatten it for me? And then you use the flatten layer as the first layer. That make sense? Yeah. And I think our code that does the numbers has a flatten layer, right? Right. There's the network for numbers. I think it has the, yeah. Okay. So so what we're gonna do besides just answer more questions about networks is look at the number classifier code in a little more detail. And then I think, hold on, let me just check on my Moodle set real quick here, because I want to make sure I have this. Sorry, give me a second. Just looking and see what we have. Yeah. Yeah, so there's going to be one more assignment. It's going to be a quiz on the code we're about to look on, and that's the end of the end of the class. Okay, and you can have until the end of finals week if you want to, but it's not that long. So, right, okay. So let's look at that code real quick, and then we're going to go look at something else. So I'm going to say I will share my screen so that you can see this in a second. Let me just get to it. Okay, let me get off this. There's kitties. Such a nice kitty.
He decided to dip out for a little bit, but I guess he's back.
He is very, very cute. And big.
Yeah.
What a good kitty. Okay, so can you see my screen? So we have our number. This again, we're just going to go through this real quick as I run it. Yeah, manage sessions. Okay, too many sessions. Why? Why do you think there's too many sessions? I don't understand. Okay. Okay. And I'm going to change this back to the default. Okay. So here what we're doing, of course, is the usual import. And then here, like I explained before, we're importing the data from TensorFlow. TensorFlow has a bunch of data sets, which is really cool. And then we're looking at the shape of the test and training sets, right? So there's the training set here, the test set, and there's 60,000 of the training sets and 10,000, 28 by 28 images. So what we saw last time. And then we're just looking at one of them, right? So you can look at, number 10 if you like, test set, right? Or the training set. Let's see what the 10th one of the training set looks like. It's a 3 probably, right? And then we're building the model. So notice here they use a flatten because this is 28 by 28 image. And they don't want to have to input like a string of, 784 numbers. They just wanted to flatten it for them. Okay. Let's take a little bit. So how many hidden layers does this have? Can you see? Do I need to make it bigger?
Does it have 2?
It does, right. So this is the first hidden layer that's right after the input. And this is the second hidden layer. They both have 25 nodes, right? And they're obviously densely connected, right? Because they're called to dense, okay. And you can see they're defining the input shape here, but it's really not necessary, okay? It's just not. This first one is necessary. Although it's possible, and I don't actually know the answer to this question, and I should try it. But it's possible that because there's a flattened layer right before it, that telling it that the input shape is 784 is redundant. That's my guess. Because if you flatten something that's 28 by 28, you're going to get something of length 784. Right. So my guess is this is redundant, just like the 25 here is redundant. Right. You'll see that in people's code. They're just possibly maybe to just make it easier for them to understand at the end. And then the dense output layer, which is 10, so that you can get, output as, it's the numbers 0 through 9. Okay. And now we're just picking the loss function here, which is this kind of special sparse category cross entropy, which you don't really need to know about. It's just one of the many loss functions you could choose. Remember in the StatQuest video, he was choosing I think it was mean squared error, right? There's just many different loss functions you can choose. And they all have their own, good points and bad points. All right, so picking the loss function, compiling the model.
Were we
Yeah.
supposed to write the pick a loss function in our homework?
No.
Okay.
No. Yeah, so you weren't supposed to go to this point, right?
Wait, which homework was this for?
The one that was due today,
Okay.
the one where you're just like setting up dense networks.
Okay.
Yeah. Okay. So the loss function here, then we're compiling the model. Remember that means telling the compiler the loss function, which is here, and then the what optimizer you want, and any metrics that you want. Okay. And now training the network using the training set. And there it goes. It's pretty fast. Evaluating the network using the test set. And it looks like the accuracy is about 89%. Not terrible, right? And then using it to predict. So notice here, when we say model.predict, all we have to give it is one of the images, right? We don't have to flatten it or anything because we have a flattened layer. Okay. So here it's just giving it number 4. And if we want to go, we can look at what number 4 is up here by going back up to this here and just see what number 4 is. I think it was the test they were just using. So let's go to test 4 and see which one it is. Of course, we could just copy this code down there too. It's a 4. Okay. So let's see what the model thinks it is. Uh-oh, what do we have here? What's happening? Oh, I know what's going on. I will have to fix this. Let me fix this and I'll put this in the last thing. Maggie, I was telling everybody there's a last homework that will be due at the end of finals week. So I forgot that I did not fix this error, so I have to fix it before I give it to you.
Okay.
Anyway,
And
but that's
also, I'm just having really
Yeah.
bad internet connection. I'm not sure. Like, I'm at school, but it just keeps going in and out.
oh no.
Is it all right if is this recording? Like, can I just watch this
is.
recorded?
Yeah, you can
Okay.
watch it. Yeah,
Thank
and we're not going to go for too much longer today anyway. So, okay, I'm going to fix that error. There's something wrong with the way I input. There is like a little funky thing that the input has to be a tensor for TensorFlow, and that's just a particular data type, and so I have to fix that. So I will fix that when we do the homework. And then we saw the live plot, right? We saw that live plot last time. So I'm just going over this again. Oh, maybe I didn't show it to you because this might have been in a video I made, so you might see it later. But anyway, so this library that I just downloaded here, right? Install live loss plot. It actually can show you the loss function as the model is run, as it's getting trained. Okay. So if we run this, so we're gonna basically train it again so you can see the live loss plot. Okay, so it's just running now. Right, so you can see that as it runs, the training data is the blue and the test data is the orange. Right, so it's training and then testing and then training and then testing. And at some point, right, very close to the end of the number of times you ask it to train, you can see that the training loss, right, goes down below the test loss. So it says validation, but it really means test because they're using the test set as the validation set. So what that means is that at this point here, you're starting to do overfitting, right? Remember that when the training loss is going below the test loss, that means like, okay, you're now starting to fit every little wiggle or wobble in the training data, and that's not going to generalize as well. So this is a good way to look at, how much should you train the model, because you can keep training it to the point where it has you know, it's following every little detail of that training set. But most likely that means that it's not going to work very well on anything else, right? So here's a good way of showing like, oh, look, this is the point where you should stop training it. This is the best you're going to get. And so this is what this live loss plot does for you, which is really nice. Okay. And then there's another part of this where this is looking at the actual weights. So remember, the weights and biases are the things that the model is training to be able to recognize those numbers, right? And if I run this, I can actually look at the weights. It's like a plot of the weights, right? And what's happening is it's looking at those weights and biases right before they are going into the last layer. And you can kind of see that there's some little patterns that the weights are picking up. Do you remember in the video, the 3 blue, 1 brown video we saw, where they were talking about how the network picks up little pieces? So you can kind of see that here, right? There's kind of little pieces of these of the numbers that you can see are being picked up by the network. I mean, it's certainly not like very intuitive though. When I look at it, I'm like, that doesn't really look like many, doesn't really look like numbers to me, but it's definitely picking up something, right? And so it's interesting to look at the weights, and sometimes it makes sense. I don't know about this. I can definitely see that there's some getting picked up, but it's not like I'm seeing like, wow, that's the shape of a 0. That's the shape of a 1. That's a shape, right? I don't see that. So it's really interesting to take a look at these weights. And this is the code that allows you to do that. So if you wanted to ever do that in the future, I'm going to share this code with you. So you should make a copy of it for yourself to keep. All right. And then the next thing I wanted to do, so this is what we're going to be working on. This code here, the basis of this code will be the basis of the homework that I'm going to be giving you, the last one. But the next thing is just fun. And that is, I got to reconnect this because it didn't like me being connected to 2 things. Yeah. Okay. Stop. I'll terminate you. It doesn't like you. I don't know why. It just decided it doesn't like. There's too many people using it right now. Okay. So this one here is called transfer learning example. It's again a piece of code that I got from this guy at Stanford, and it's a cat versus dog classifier, which is really fun. It's a complicated network. It's not as simple as the one for numbers. It is really very optimized. It does very well. There are other versions of that number classifier that actually do a lot better than the one we just saw. But it's the simplest version of the one we just saw is the simplest version of the number classifier. But there are much better networks for number classifications that are used in like actual industry, optical character recognition. Okay, so this is more of a state-of-the-art type network. So again, the same kind of thing. We're importing TensorFlow and Keras and NumPy, right? All start the same. There's a lot of little things here that are being that are being imported. There's mobile net, which is a particular network, a particular neural net. There's all kinds of other things that are being imported here for this network. Okay, I'm just going to run through a few of these. They're actually importing the weights from the mobile net. So in other words, this is a network that has been trained with millions of cat and dog images, of labeled cat and dog images. So this code right here is not going to train that network. It's literally downloading the weights from that network that's already been trained on millions and millions of cat dog pictures. So once you download the weights, then you can run the model, right? So weights and biases, right? So that's what this is doing. And it's got 87 hidden layers. So again, we're taking a look at this. This is a state-of-the-art network. So 87 hidden layers. That's one of these things that people call a deep learning network, right? So if you ever hear the term deep learning, they're talking about a neural network that has many, 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 like 87 hidden layers. Okay. Actually probably has 85 hidden layers because there's an input and an output, but right, still it's huge numbers of layers. And then if we look at the model summary here, right, the base model, this is the model that has already been trained for cats and dogs. It's got a bunch of crazy layers, right? So it's not just these densely connected layers. There are these layers that are called convolution layers that do the special operation on the weights and biases before passing it on. Okay, so really complicated, very different from these densely connected layers. And sort of like I said, this is more state of the art, right? This is where the networks, the first ones you were looking at for the numbers, that's like pretty basic. This is the state of the art. Again, very deep networks with these convolutional layers that do a lot of this sort of math on the weights and the there's kind of forward propagation and back propagation of the weights and biases. So it's really quite complicated, and you can see it's quite big. There are 3 million parameters that are trained in this network. Okay, a lot. So it's a huge network. And again, this is why we're not going to train it here, right? We're literally downloading the weights because it's been trained already. Probably took a very, very long time to train. Okay. And now we're just adding some new layers to the network. Okay, we're just going to add some more fully connected layers on top, and they're just so that we can run this, really. Okay, so that's what's done here. Right, and then and then only these top layers are the only ones going to be trained. So basically, it's kind of like this big network where it was trained. We have all this weights and biases. We have that base network, and then we're going to just add a couple layers on so we can use it to play around with. Huh? Okay. And that's what we're doing here. Right. And we've added a couple layers, so now we have 93 layers. Okay.
So, Dr. Shank, is the last quiz going to be asking us to write code like this, or is
No.
Oh, okay.
No, I'm showing you this because we're not going to get to this level in this class, right? This is not something we would ever probably get to in this class. Okay. So I just want to show you what sort of a state-of-the-art code looks like. Okay.
Oh,
yeah.
Okay.
Yeah,
You're not freaking me out.
No. It's sort of state-of-the-art, and plus it's a fun code, so we're going to play with it in a minute. So we're now downloading a bunch of data, and that just means like a bunch of pictures of cats and dogs. Okay. And just making sure that we are getting all the data ready and processed. And here's one of the images. This is cat 30. Can you see kitty 30? And let's see what kitty 100 looks like. Oh, that's a very cute one. So these are the training images, right? So these are and you can see here it says this is cats and dogs filtered, train, right? So it's the training set and it's the cats. So we want to look at dogs. We can probably say here, the training set for dogs, and let's look at dog 100 and see what he looks like. There's dog 100. Yeah. So these are the training data, right? Okay. And we're just gonna tell it, to define the training set, etc. Just running a few things before we get to the actual training the model. Again, we're not training the full model. We're training like a little piece of it. Yeah. So it's got to take its time a little bit for a second here. There we go. It's only doing 5 epochs of training because we're actually only training like the new layers we put on. We already had the weights from all the other 87 layers, right? Okay. So let's train it, and then we're going to play with it. Just going to take a little minute. As you can see, it's going through 5 epochs of training. And the accuracy is already super, super high. As you can see, the accuracy is 98% because we already had a fully trained 87-layer model behind it. Right? That's why this is called transfer learning, because you're sort of transferring the learning from the big network to this little, to the layers that you just added on, you know? So we're really only training these new layers. Okay, looks like we're done. We have a 99.2% accuracy here, and let's test the model. Okay, so here's a kitty. This is kitty 2001. Let's see. There's image kitty 2001, and let's use that image to predict whether the network thinks that's a cat or a dog. Okay, so if you see here, I don't know if you can see this, but here's kitty. And the network was used to model, predict, and then the image was put in, right? And then what you got out of the network is a probability, right? So it's 0.99% sure that it's a cat, and only 2.5 times 10 to the minus 5% sure it's a dog. So it's pretty darn sure it's a cat, right? So that's how these things work, right? They're not going to absolutely say 100% cat, right? They're going to say, well, I'm 99.9975% sure it's a cat, right? Okay, so let's look at another. Here's a dog image, and let's predict on that. Well, it's 99.36% sure that's a dog, right? And only 0.006. Well, actually, that would be 0.6% sure that it's a cat, right? So it's not quite as sure. Okay. Now here, there's another thing that we're going to do here, which is just to make it output how sure it is. Here, when we do these, when we use model.predict, it's putting out these numbers, and we have to look at them and be like, oh yeah, okay, I see that it thinks it's a dog, pretty much. But we're going to just make a little file, a little thing here that will tell us how confident is it that it's a dog. Okay. And now here, I'm going to do it on our dog 2000. And it says it's 99.44% confidence it's a dog. Okay. Okay. All right. Now this code here is one where we can upload our own picture of a cat or a dog. So I'm going to go and browse my folder. I already got a cat. This is not my cat. Well, actually, here's my cat right here. I don't know if you can see. This is a picture of my cat right there. And I'm going to double click on her and see what the image, what it thinks. So it's uploading. And it's 100% confident that it's a cat. That's my cat. So I'm going to be sharing this one with you as well. And I want you guys to, so it's you have to run the whole thing. And then down here at the bottom is where you can upload your own picture of your cat or your dog, or a cat or dog that you got from the internet, right? And see if you can stump the code, right? See if you can find an image that's not gonna work, that is a cat or dog, but the network doesn't.
What? So this might have already spoiled it, but would it work for cartoon images?
That's a really good point. Let's see. I had one downloaded. Let's see what happens. So I'm going to run this. You have to run this every time and then browse.
Because then you can do the cat dog from.
Yeah, right here, dog cat.
You can't be a dog.
Yeah, I got that one.
Yes.
It's 51% confidence. So yeah. So there you go, right? Because it's cat dog. Yeah. So, it's really quite amazing because this network is a deep learning network that's these, the sort of state-of-the-art convolutional networks. It works really, really well, right? But there are certain things that are going to stump it, right? That, not cat dog, because obviously we can't say what that is, right? You can't look at cat dog and be like, well, that's a cat, right? So if you can't tell, then the network's definitely not going to tell. But it really does quite amazingly well. So I'm going to give you this again. Whenever I give you a network, make sure that you make a copy of your own. Okay, name it something else and make it, because anytime you change anything I share with you, right, it'll change on my end too. So make sure that you're making your own copy. Okay. All right. So this video that we're making now will just serve as your walkthrough of this, because all I want you to do with this particular one is to run some images through it and see if you can stump it. Right. So find some images on the web, take some images yourself. It often is really interesting to see what happens when there's other things in the photo. So when there's like a human in the photo, what happens, right? There might be like, a picture of a cat, but then there's kind of a dog butt in half the photo or something, right? I wonder what happens, what happens with that. So it'd be interesting just to see how well this does. But again, this is state-of-the-art deep learning network that was trained with millions of these labeled cat dog things. So it does really amazing. And this is kind of represents, like I said, state-of-the-art for image classification. Okay. I think, did you have a question?
Yeah, so that's just basically what this last quiz is seeing if we could.
Well, that's part of it. The other one is
Okay.
doing some work with the other code I just showed you with the numbers, but yeah. So with the number code, but the last part of it is seeing if you can stump it. Show me, and then upload the image that it did like the worst on, right? And see if you can tell me why you think it did the worst on that. But it's fun to try to stump them, But it's really quite amazing how well it does. So yeah, again, this is the state of the art. But it's nice, you'll have this code, so you'll have an idea of what, and this is, again, transfer learning means that somebody already trained a really deep network for you, and then you would sort of tack on some layers, and now that whole network you can train on your own. You know what I mean? Yeah. Okay. So I will do all that, and that's pretty much it for today. We don't have to go all the way to the end. Got about 10 minutes anyway. Any questions?
I have like a little side.
Yeah.
Like if we, by us adding images that we're trying to stump the program, does it add to it, or
it doesn't? No, that would be cool. But the data set that we've got here is just a set data set that is not going to be like changed by us adding images in. Yeah, that'd be cool though, right? But you could add in. But they want to validate whenever they have a data set like this that's already been used to train a big network. They want to make sure that that the labeling doesn't get corrupted, right? So someone could come in and be like, I'm going to label all cats dogs, and then now you're like ruining the network, right? So they don't want people to upload anything. There are big data. I can't remember if I showed you a video of this woman who is building these big data websites where people can contribute to labeling data. I can't remember if I showed you a video of her, but she did a TED talk. She's at Stanford as well. So the idea.
I think that was one of the first videos you showed us.
I think so too. Yeah, I vaguely remember that. So she's trying to do this kind of thing where people come in and label, but then there's lots of people who validate that afterwards, because this is a big job, like trying to because you have to label using a human. A human has to label the stuff, right? So it's kind of arduous, Make sense? All right, guys. Well, thanks for being in class, and I hope that you can end up using some of this code and stuff in future jobs. And you may not remember it all, but you'll have the code, right, and the book. So that should be helpful, hopefully, at some point. All right. We'll talk to you later.
Thank you.
Bye.
Thank you.
Bye.